Welcome to today's problem walkthrough. In this session, we will tackle LeetCode problem number 1313, titled Decompress Run Length Encoded List. This is a beginner-friendly problem that tests your ability to work with arrays and implement basic decompression logic. Let's dive in and explore the approaches to solve this task. In this problem, we are given an array called nums, which is structured as a run-length encoded list. The idea here is that each pair of adjacent elements in the array represents two things. The first number, frequency, specifies how many times the second number, val, should appear in the decompressed version of the list. For every pair, frequency, val, frequency tells us the frequency, and val is the value we need to repeat. Our job is to take this encoded array, decompress it, and return the resulting array. The input will always be an even-length array because it consists of n pairs, where frequency and val alternate. The output should be a single array containing all the values repeated according to their frequencies. Let's look at an example to clarify. If the input array is nums equals 1, 2, 3, 4, we interpret this as two pairs, 1, 2, and 3, 4. For the first pair, frequency equals 1 and val equals 2, so we decompress it to 2. For the second pair, frequency equals 3 and val equals 4, which decompresses to 4, 4, 4. When we concatenate these segments together, we get 2, 4, 4, 4 as the output. Another example is nums equals 5, 1, 2, 3. The first pair, 5, 1, gives us 5 instances of 1, resulting in 1, 1, 1, 1, 1. The second pair, 2, 3, gives 2 instances of 3, resulting in 3, 3. Combining these, the output becomes 1, 1, 1, 1, 1, 3, 3. Now consider the case where nums equals 10, 7. Here, there is only one pair, 10, 7, meaning frequency equals 10 and val equals 7. This tells us to repeat the value 10 times, resulting in a decompressed segment of 7, 7, 7, 7, 7, 7, 7, 7, 7, 7. Since there is only one pair in the input, this segment is the entire output. The constraints of the problem ensure that the input length is always even, so the structure of the problem remains consistent, and every pair can be processed independently in this way. The problem also defines a few constraints and edge cases to consider. First, the array length nums.length will always be between 2 and 100, and it will always be even. Each integer in the array will fall between 1 and 100. For the smallest input size, such as nums equals 1, 1, we have one pair, 1, 1, which decompresses to 1. This demonstrates the minimum possible output size of 1. On the other hand, for a maximum frequency, such as nums equals 100, 5, the decompressed array will contain the value 5 repeated 100 times. These constraints ensure that we can handle both small and large outputs efficiently. Finally, let's look at an example with multiple pairs and varied frequencies. If nums equals 2, 3, 1, 4, 3, 2, we break it into 3 pairs, 2, 3, 1, 4, and 3, 2. The first pair, 2, 3, decompresses into 3, 3. The second pair, 1, 4, decompresses into 4. The third pair, 3, 2, gives 2, 2, 2. When we concatenate these segments, the result is 3, 3, 4, 2, 2, 2. This example illustrates how the decompressed list is constructed by processing each pair in sequence and combining their results. By handling each pair independently, we can easily build the final array step by step. To solve this problem, one natural approach is the brute force method, which we can think of as a direct expansion of the input. The key insight is that the problem explicitly tells us how to decompress the list. Each pair in the input, represented as frequent val, provides the frequency of a value and the value itself. The steps are simple: initialize an empty list, iterate through the input in steps of 2 to extract each frequency and val, and then append frequency copies of val to the result. Finally, return the resulting list. This approach works well because it directly mirrors the problem's requirements. However, it has a potential drawback. If frequency is very large, appending repeatedly can introduce overhead due to dynamic resizing of the list. While the time complexity is O(n), proportional to the length of the decompressed list, and space complexity is also O(n), this method may not be the most efficient for all scenarios. Another, more concise approach is to use Python's list comprehension feature. This optimized method allows us to generate the decompressed list in a single line. Instead of manually iterating and appending values, we iterate over the input in steps of 2 and, for each pair, frequency, val, create frequency copies of val inline. These smaller sublists are then flattened into one complete list. The entire process is efficient, as list comprehensions are designed to handle such operations effectively. The time complexity remains O(n), as we are still expanding each frequency copies of val, and the space complexity is also O(n). The main advantage of this approach is its simplicity and readability, which makes it easy to implement while leveraging Python's optimized handling of list operations. An alternative strategy involves pre-allocating the output list to avoid the overhead associated with dynamic resizing. The idea is to compute the total size of the decompressed list in advance by summing up all the frequency values from the input. Once the size is known, we create a list of this exact size and populate it directly. This eliminates the need for repeated appending. The steps include calculating the total length, initializing the pre-allocate list, and then iterating through the input to fill the list with the corresponding val values. This approach maintains an O(n) time complexity for both pre-allocation and filling, and the space complexity remains O(n). The advantage is improved performance for very large inputs, but it does come at the cost of increased code complexity compared to the other methods. After evaluating the different strategies, we chose the list comprehension approach as our preferred solution. It is concise, straightforward to implement, and takes advantage of Python's built-in optimizations for list operations. While the pre-allocation method could offer slightly better performance for extremely large inputs, the difference is minimal in most practical scenarios. The brute force approach, although simple and intuitive, involves manual appending, which can lead to dynamic resizing overhead and is less elegant overall. By contrast, the list comprehension approach strikes the perfect balance between readability, simplicity, and efficiency. It is ideal for most use cases, making it the best choice for this problem. Overall, the trade-offs highlight the strengths of each method, but the practicality and elegance of list comprehension make it the clear winner for this task. Here, we're tasked with decompressing a run-length encoded list. The input, nums, is given in pairs of frequent, val, where frequency represents how many times the value val should appear in the output. To solve this, we'll follow a systematic approach. First, we initialize an empty list called result to store the decompressed values. This list will be our final output. Next, we iterate through nums in steps of 2, treating every 2 consecutive numbers as a frequent, val, pair. This allows us to focus on processing each pair directly. For each pair, we extract frequency and val, then generate a sublist containing frequency copies of val. We achieve this efficiently in Python using list multiplication. Finally, we append the generated sublist to result, gradually building the decompressed sequence pair by pair. Now, as we continue, the next step is to combine all the sublists into our output list. Each pair contributes a chunk to the result list, which dynamically grows as we process more pairs. By the end of the iteration, result will hold the complete decompressed sequence. Once all pairs have been processed, we simply return the result list as the final decompressed array. A few key insights make this algorithm efficient and straightforward. First, the structure of the input is predictable. The list always contains even-length pairs of frequent, val, which makes it easy to iterate and decompose. Second, Python's list multiplication allows us to generate repeated values without manually looping, which saves us time and effort. Lastly, the dynamic nature of Python lists means we don't need to pre-compute the total size of the output, simplifying implementation. In terms of data structures, the input is a sequential list of integers, and the output is another list that grows dynamically as we append decompressed values. Now let's discuss some important edge cases and the complexity of the algorithm. First, if the input list is empty, the output should also be an empty list since there's nothing to decompress. For a single pair, such as 1, 7, the algorithm should correctly handle this minimal case and produce 7 as the output. Additionally, the algorithm must handle large frequencies, such as 10⁻⁴, efficiently. Python's list multiplication is well suited for this because it avoids manually iterating frequency times, but we need to remain mindful of memory limits for very large inputs. In terms of performance, the time complexity is O(n), where n is the length of the decompressed list, since we append frequency elements for each pair. The space complexity is also O(n), as the output list grows proportional to the decompressed size. Here's the complete implementation of the algorithm in Python. We define a function decompressRLList that initializes an empty result list. Then, using a loop that iterates in steps of 2, we extract frequency and val from the input, generate a sublist of repeated values using val *frequency, and extend the result list with this sublist. Finally, we return the result. Let's walk through an example to see the algorithm in action. Suppose the input is nums equals 2, 3, 1, 4. We start by initializing an empty list, result equals. First, we process the pair 2, 3. Here, frequency equals 2 and val equals 3, so we create a sublist 3, 3, and append it to result, resulting in result equals 3, 3. Next, we process the pair 1, 4, where frequency equals 1 and val equals 4. This gives us a sublist 4, which we append to result, producing the final output 3, 3, 4. While this approach is straightforward, we can optimize it in certain scenarios. For instance, if we pre-compute the total size of the output by summing all frequency values, we could pre-allocate the result list. This avoids the overhead of dynamic resizing but requires an additional pass through the input. However, this optimization may be unnecessary for most typical inputs. One limitation to keep in mind is that for extremely large inputs, memory constraints could become a bottleneck, as the algorithm constructs the entire decompressed list in memory. This Python implementation solves the LeetCode problem number 1313, decompress run length encoded list. The task is to decompress a given list of integers in the format frequency 1, val 1, frequency 2, val 2, where each pair, frequency, val, represents frequency instances of the integer val. The goal is to expand the list explicitly. ###explanation. 1. Class and method definition. We define a class solution and a method decompressRLList within it. The method takes a single argument nums, which is the input list. 2. Initialize result list. We create an empty list named result. This list will store the decompressed values. 3. Iterate over pairs. The loop iterates over the input list nums with a step size of 2, indices 0, 2, 4. This ensures we process each frequent val pair sequentially. Frequency is assigned the value at the current index, nums, I, and val is assigned the value at the next index, nums, I plus 1. 4. Expand values. For each pair, we append frequency copies of val to the result list. This is achieved using list multiplication, val, *frequency, to create a list of frequency repeated values, followed by the extend method to concatenate it with result. 5. Return result. After processing all pairs, we return the result list, which contains the fully decompressed sequence. ###edge cases. If nums is empty, the method handles it gracefully by returning an empty list. The problem guarantees that nums has an even length and valid values, so no additional validation is required. ### complexity. Time complexity, O(n), where n is the length of the input list. Each pair, frequent, val, is processed once, and the list concatenation takes linear time relative to the total number of elements in the output. Space complexity, O(m), where m is the total number of elements in the decompressed list, as we store the result explicitly. This implementation is efficient and adheres to the constraints, ensuring correctness for all valid inputs. This is the Java implementation of the decompress run length encoded list problem, mirroring the logic of the Python solution. The solution uses a dynamic arraylist to manage the decompressed elements and iterates through the input array in pairs, appending the appropriate number of elements to the result list. The list is then converted to an array for the final output using Java Stream API. The key differences from Python include the use of explicit type declarations, Java collections like ArrayList, and conversion of the list to a primitive array for the return value. In this problem, we are tasked with decompressing a run length encoded list. The input list, nums, has an even number of elements where the values at even indices represent frequencies, and the values at odd indices represent the corresponding elements. The goal is to generate a new list where each element appears as many times as its associated frequency, in the order given. For example, if nums is 1, 2, 3, 4, we start by initializing an empty list called result to hold the decompressed values. We then process the first pair of values, where the frequency is 1 and the value is 2. Using list multiplication, we append one copy of 2 to result, which now becomes 2. Next, we move to the second pair of elements in nums. Here, the frequency is 3 and the value is 4. Again, we use list multiplication to append 3 copies of 4 to result. This operation creates the sublist 4, 4, 4, which is added to the existing result, making it 2, 4, 4, 4. At this point, we've processed all pairs in the input, and the final decompressed list is 2, 4, 4, 4. Let's consider another example where nums is 2, 5, 1, 6. As before, we start with an empty result list to store the decompressed values. For the first pair in this example, the frequency is 2 and the value is 5. Using the same approach, we append 2 copies of 5 to result, resulting in 5, 5. Then, we process the second pair, which has a frequency of 1 and a value of 6. Here, we append 1 copy of 6 to result, extending it to 5, 5, 6. With all pairs processed, the final decompressed list for this example is 5, 5, 6. Now, let's look at another example with a smaller input to reinforce the steps. In this example, the input nums is 4, 7, so we again initialize an empty list result. For the first pair, the frequency is 4 and the value is 7. Using list multiplication, we append 4 copies of 7 to result. This operation creates the list 7, 7, 7, 7, which represents the final decompressed output since there are no additional pairs to process. The resulting list, 7, 7, 7, 7, demonstrates how the algorithm handles scenarios with a single pair of frequency and value. To summarize, the algorithm processes the input list in steps of 2, ensuring that each frequency and its corresponding value are handled sequentially. By directly extending the result list with val *frequent, we efficiently append the required repetitions of each value. The time complexity of this solution is O(n), where n is the size of the input list, as we iterate through the list once and use efficient list operations. Some key edge cases to consider include an empty input list, which results in an empty output, and cases where all frequencies are 0, which also produces an empty output. This solution is designed to handle all valid inputs within the problem constraints, such as ensuring the input length is even and all values are within the specified range. To analyze the time complexity, we start by considering how the input list nums is processed. The code works in pairs, where each pair consists of a frequency, and a value, val. The for loop iterates through nums in steps of 2, meaning the total number of iterations is half the length of nums. If the size of the input list is n, the loop executes n/2 times. For each pair, the algorithm creates a temporary list of size frequency, containing copies of val, and extends the result list with this temporary list. The cost of extending result depends on the frequency for that pair. If we denote the frequencies as f_1, f_2, f_k, the total cost of appending these lists to result is proportional to the sum of all frequencies, f_1 plus f_2 plus f_k. The overall time complexity is now determined by the sum of all frequencies. This total of f_1 plus f_2 plus f_k corresponds to the size of the decompressed output list, which we call m. Since the for loop processes the input list in n/2 iterations and each iteration contributes a cost proportional to frequency, the total cost of the algorithm is directly proportional to the size of the output list. Thus, the time complexity of the algorithm is O(m), where m is the size of the decompressed list. For space complexity, let's first consider the auxiliary space. The algorithm creates a temporary list, val *frequency for each pair, which requires frequency space. However, since this temporary list is discarded immediately after it is used to extend the result list, the auxiliary space usage does not grow with the input size, making it O(1). The output space, on the other hand, is proportional to the size of the decompressed list, M, as the result list stores all M elements. Combining the auxiliary space and the space required for the output, the overall space complexity is dominated by the size of the result list. Therefore, the total space complexity is O, M, where M is the size of the decompressed list. To compare this solution with a brute force approach, consider what happens if we append frequency copies of val one at a time instead of using bulk list extension. While the time complexity remains O, M, for both approaches, the given solution is more efficient in practice because it performs bulk operations, reducing the overhead of repeated method calls. By creating and extending with a temporary list, the given solution minimizes intermediate operations, making it faster and more practical while maintaining the same asymptotic efficiency. Now, let's break down the best, worst, and average case scenarios. In the best case, all frequencies in nums are small, meaning the output list size is relatively small. Even in this situation, the time and space complexities remain O, M, as they depend solely on the size of the output. In the worst case, frequencies are large, which means the output list grows significantly. Despite this, the time and space complexities do not change, they remain O, M, as they scale with the size of the decompressed list. On average, the time and space complexities are still determined by the distribution of frequency values, but the asymptotic complexity remains O, M, for any input distribution. This consistency across all cases highlights the robustness of the algorithm's performance. Let's go over some common mistakes that can occur when solving this problem. First, incorrect index handling is a frequent issue. Since the input list is structured in pairs, iterating element by element, such as using for in range, len, nums, can lead to accessing invalid indices. The correct way is to iterate in steps of 2, like for in range, 0, len, nums, 2. This ensures you are always processing frequency, val, pairs. Another common mistake is excessive memory usage during intermediate steps. For example, repeatedly appending values with res plus equals, val, asterisk frequency creates new lists at each step, leading to inefficient O, n squared, time complexity. Instead, it's better to use operations that modify the list in place. Finally, misunderstanding the input format can also lead to errors. Assuming all inputs are integers or failing to validate that frequency is non-negative might cause runtime crashes or infinite loops. Always adhere to the problem constraints to avoid these issues. Overcomplicating edge cases is another frequent mistake. Situations like an empty input list or a single pair, such as nums equals 1, 5, are often mishandled. Some solutions introduce unnecessary conditionals for these cases, which isn't needed. A robust iteration structure can handle these scenarios naturally. Additionally, ignoring output constraints is problematic when dealing with very large inputs. For instance, if frequency values are in the range of 10,000, failing to account for memory limitations can slow down performance significantly. Always ensure your solution is optimized and can handle the upper bounds of the constraints effectively. From an interview perspective, this problem is a great example of pattern recognition. The key insight here is understanding that the input is structured in frequency value pairs, which is a common pattern in array manipulation problems. Another focus is efficiency. Interviewers often look for solutions that minimize memory usage and avoid redundant computations. Constructing intermediate results unnecessarily is something to avoid. Testing edge cases is also essential, as they frequently reveal overlooked bugs. Demonstrating thorough testing during an interview showcases your attention to detail. Lastly, scalability is important. When discussing your solution, highlight trade-offs and consider optimizations like in-place operations to save space when working with large inputs. This problem shares similarities with other LeetCode problems, which can help you build your problem-solving toolkit. For instance, LeetCode 443, string compression, involves a similar frequency-value relationship for compressing or expanding data. LeetCode 1313, the decompress run-length encoded list problem itself, can have variations in constraints but uses the same core logic. LeetCode 1029, two-city scheduling, involves pairing elements and optimizing based on constraints, which is a different but related pattern. Lastly, LeetCode 167, twosome2, focuses on leveraging input structure for efficiency during iteration over pairs. Exploring these related problems can deepen your understanding of pairing and iteration strategies. There are several alternative approaches to solving this problem, each with its own trade-offs. The brute force expansion method involves directly iterating over the array in pairs and appending val * frequency to the result. While simple to implement, this approach becomes inefficient for large frequency values due to repeated appending. A more efficient alternative is pre-allocating the result array by calculating the total size of the output first and then filling it iteratively. This saves time during the expansion process but requires additional logic to compute the size upfront. Another approach is using a generator-based solution, which yields values lazily. This is memory efficient and avoids creating large intermediate lists, but it may require converting the generator to a list later, which adds some overhead. Each method has its pros and cons, so choose the one that best aligns with the problem's constraints and requirements. Great job working through this problem. We reviewed the decompression logic for run-length encoded lists and implemented a straightforward brute force approach. Remember, this problem is an excellent opportunity to practice array manipulation and edge case handling. Thank you for watching, and don't forget to like and subscribe for more coding tutorials. Keep practicing and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!